7,500 light-years from here, there is a star that has already died once. In March 1843, Eta Carinae blew off at least 10 times the mass of our Sun, 3,000 Jupiters worth of itself, at hundreds of kilometers per second, and briefly became the second brightest star in the entire night sky, beaten only by Sirius. By every measure physics has, that should have been the end of it. It was not. The star is still there. We photograph it every year. Astronomers call that event the Great Eruption, and it remains the strangest thing a star has been caught doing at close range. It released roughly 10% of the energy of a typical core collapse supernova. It stripped away a chunk of the star large enough to build 10 suns, and then the star went on living. Eta Carinae was not a stranger before that night. It had been catalogued long before and had spent generations varying modestly in brightness, the sort of star that gets a designation and then gets ignored. Then, in 1837, something changed, and over the next few years, it climbed to apparent magnitude -1. The shedding did not stop with the peak. It continued for about 20 years, and estimates of the total mass thrown off across the whole event run from 10 solar masses at the low end to several times that at the high end. No supernova ever appeared. The ejected material did not disperse. It expanded into a visible nebula, now called the Homunculus, named for its faint resemblance to a small human figure in early photographs. The Homunculus is two distinct lobes of glowing material separated by an equatorial disk, expanding outward from the central star at a rate that allows astronomers to date the original ejection precisely to the 1843 event. The Homunculus is, in effect, a frozen-in-time photograph of an explosion that was supposed to have killed Eta Carinae, but did not. The star survived. The brightness faded over the following decades. By the late 1860s, Eta Carinae had returned to roughly its pre-eruption brightness, but its appearance through telescopes was permanently changed. It was now embedded inside the rapidly expanding Homunculus nebula. The star itself was harder to study directly, hidden behind the very debris it had produced. For 150 years afterward, Eta Carinae remained quiescent, variable but stable. It became one of the most studied stars in the southern sky, observed continuously by every generation of new astronomical instruments. The Hubble Space Telescope photographed it. Chandra observed it in X-rays. The Very Large Telescope imaged the Homunculus in fine detail. Yet despite all that scrutiny, the central question of what Eta Carinae actually is and what it will do next has not been definitively answered. But here's the part that makes Eta Carinae genuinely unusual. It is not one star. Every measurement of that eruption, every model of what survived it, has to account for two. Eta Carinae is, by all available evidence, a binary system. Two extremely massive stars orbiting each other in a highly elliptical orbit with a period of just over 5.5 years. The primary star, Eta Carinae A, is a luminous blue variable, a class of star that contains the most massive and luminous stars known. Its current mass is estimated at roughly 90 to 120 times the mass of our Sun, after the substantial losses of the 1843 eruption and the slower stellar winds that have continued since. Its luminosity is approximately 5 million times that of our Sun. The companion, Eta Carinae B, is a hot, massive star in its own right, with a mass of roughly 30 to 80 solar masses and a luminosity in the high hundreds of thousands of suns. Eta Carinae B is a star that, in any other context, would be considered one of the most extreme objects in the galaxy. In this system, it is the supporting actor. Stars of 100 or more solar masses should not exist for long. The theoretical maximum mass at which a star can stably fuse hydrogen, the so-called Eddington limit, is debated, but most models place it somewhere between 100 and 150 solar masses. Above that limit, the star's own radiation pressure overcomes its gravitational binding, and the outer layers are blown off into space at extreme rates. Eta Carinae A sits right at the Eddington limit, and several models place it above. It is shedding mass continuously through stellar winds. It is unstable on a timescale of tens to hundreds of thousands of years. When such a star finally exhausts its core fuel and begins core collapse, the resulting event is not an ordinary supernova. The progenitor mass is too high. The collapse produces what astronomers call a hypernova, a supernova with energy output 10 to 100 times higher than a typical core collapse event. Hypernovae are often associated with gamma-ray bursts. They produce the most extreme stellar explosions in the modern universe. And this is where the story stops being an astronomy curiosity and starts involving us. Eta Carinae is, by any reasonable accounting, the closest candidate for a hypernova in the local stellar neighborhood. The star is approximately 7,500 light-years from Earth. If it produces a hypernova, the burst of high-energy radiation reaching Earth would be significant. Whether it would be dangerous depends on a critical factor: the orientation of the rotational axis of the star. If the rotational axis is pointed away from Earth, the gamma-ray burst, if there is one, will be directed elsewhere, and Earth will experience only the ordinary, distant supernova event, a bright new star in the southern sky, fading over weeks. If the rotational axis is pointed even partially toward Earth, the consequences are more serious. A gamma-ray burst from 7,500 light-years away, with the energy of a hypernova, would deposit enough high-energy radiation in the upper atmosphere to substantially disrupt ozone, increase ground-level UV exposure, and potentially affect biospheric chemistry for years afterward. Recent observations indicate that the rotational axis of Eta Carinae is most likely not pointed at Earth. The orientation appears to be tilted significantly off-axis. The probability of direct gamma-ray exposure is low, but low is not zero, and the orientation is not measured with perfect precision. We do not know when Eta Carinae will explode. The 1843 eruption was not the explosion. It was a precursor event, a sign that the star is in its terminal phase, that it is shedding mass at unsustainable rates, that it is approaching the end of its stable existence. Stars in this regime do not always die quickly. Some massive stars are observed to exhibit luminous blue variable eruptions for tens of thousands of years before final collapse. Some die within a few hundred years of the first major eruption. Eta Carinae has been in this final state since the 1830s, about 200 years and counting. By the standards of stellar evolution, it could survive for tens of thousands more years. By the standards of stellar evolution, it could collapse tomorrow. The best modern estimates, based on detailed modeling of the interior structure inferred from observations, place the most likely time of final collapse somewhere within the next 100,000 years. That is a wide window. It is also, in cosmic terms, immediate. Eta Carinae is one of the few stars where the supernova is genuinely imminent on human-relevant timescales. When it does explode, the supernova will be unmistakable. At 7,500 light-years, the apparent magnitude could reach somewhere between -4 and -8. At the bright end of that range, enough to cast shadows at night, certainly bright enough to be visible during the day for weeks. It will be the most spectacular astronomical event in the recorded history of the Southern Hemisphere. Cultures with continuous astronomical record-keeping, and at the rate civilization is changing, that may include cultures we have not yet imagined, will record it as a fundamental marker in their sky. The remnant will be a neutron star or black hole, depending on how much mass Eta Carinae has lost by the moment of collapse. The Homunculus nebula will be disrupted by the supernova shockwave, creating a new, larger nebula that will be visible for thousands of years afterward. Heavy elements, forged in the final fusion stages, will be returned to the interstellar medium. And the questions about Eta Carinae, what it is, why it survived 1843, what makes a star at the Eddington limit behave the way it does, will be answered in the moments after the explosion, in observational data that will be used to refine our models of massive stellar evolution for centuries afterward. We are waiting for a star to die that has been trying to die for 200 years. The wait could end at any moment.